CPUs live in a fantasy land. Some onboard crystal feeds their clock input, and they dutifully process instructions according to that clock with incredible consistency. Solid-state helpers like RAM and graphics cards run at compatible speeds and know how to keep from stepping on the CPU's toes whenever they need to access the bus. And then there are the machines, with their motors and servos and solenoids, and their annoying deference to things like physics and the real world. They don't respect the CPU's fantasy. They are real buzzkills. Today we're going to explore what happens when these two worlds collide. How can the CPU and a floppy drive synchronize their work and have a nearly flawless interchange of data? And how did folks make this work back in the 80s, when not everything was digital yet, and things ran relatively slow compared to modern machines? Some of their choices were surprising. Then we'll hack the implementation to simplify things, to see whether the complexity was really necessary. We'll be investigating the computer floppy drive interface exactly as it was designed on the TRS-80 Color Computer. Note that there is no floppy drive port on the CoCo. In fact, many people never bought a floppy drive at all and did all of their saving and restoring using the slow tape recorder. I was stuck using this for many years, and I can tell you it was problematic. If the tape wasn't running at exactly the right speed or the volume wasn't quite right, you would get all sorts of errors. And the transfer speeds were slow. It could take 3 minutes just to load up a game. So if there's no floppy drive port on the CoCo, how do we actually connect the floppy drive to the CoCo? Want to play a game of Poltergeist? The CoCo has a cartridge port. This allowed game makers to produce cartridges with the game code burned into a ROM chip inside. The cartridge port had all of the usual pins you'd expect, including 16 address lines, 8 data lines, and a read-write line, so that the CPU could execute instructions off of the ROM inside. If you booted the CoCo without a cartridge plugged in, it went straight to the BASIC interpreter. Because in those days, the assumption was that if you owned a computer, you probably wanted to write code for it. But what happens if you try to run a disk command, like dir, which shows the contents of the floppy directory? Obviously, we get an error, but the SN error doesn't mean that it couldn't find a floppy or it couldn't find a floppy drive. This is a syntax error. It literally has no idea what we're talking about when we type dir. Enter the floppy drive cartridge. This includes a ROM chip which extends the BASIC interpreter to understand the disk commands. You might have noticed that the startup message now has the word disk in it. And if I type dir, well, we still get an error because I didn't turn on the floppy drive, but it's no longer a syntax error. It knows what we're talking about and it's trying to do it. Fun fact, Poltergeist was neither directed nor written by Steven Spielberg, but he did write all the code for this game.
CoCo Town fact!
Not a fact. Let's take a look inside the cartridge. On the left, we see all of the lines coming in through the cartridge pins. A lot more than most games would ever need to use. And on the right, we see the pins that go out through the ribbon cable and onto the floppy drive. Somewhere in the middle, of course, we see the ROM chip that implements all of the disk commands like dir. There's a lot more in here, and we'll return to discuss it in more depth. But first, let's take a look at the computer side of this, and we'll start with NMI.
There's a party in my tummy.
So nummy.
Floppy data bytes are yummy.
So nummy.
There's a floppy in my tummy.
So nummy.
There's a party in my tummy.
So nummy.
The CoCo comes with a 6809 CPU, and it's capable of several kinds of interrupts. In a previous video, I went into great detail on the IRQ interrupt, as that is extremely important for game programming. It allows the drawing code to sync up with the TV's electron beam. Here's a quick review of the IRQ, though you might want to check out this video later if you want to go deeper. The IRQ represents a field sync or vertical sync from the video display generator, or VDG. That means the IRQ interrupt is raised when the electron beam in the TV gets close enough to the bottom of the screen that it's just outside the viewable area. This is shortly before the TV's blanking interval starts, which is when the program has the maximum amount of time to fill up the frame buffer with the appropriate pixels before the TV needs to draw them. A few things need to happen for the IRQ to be raised. First, the video display generator determines the time is right. Next, the VDG signals one of the peripheral interface adapters, or PIA, that it's field sync time. Then the PIA consults its hardware registers to decide if it should notify the CPU or just ignore. Software like games program those hardware registers so they can enable or disable the IRQ. Assuming the PIA signals the CPU, there's one last gate to pass through, and that's the condition code register flags, specifically the I flag. If that I flag is set, then the IRQ is considered masked, which means the CPU will ignore the interrupt. Otherwise, the CPU will interrupt its execution sequence of instructions as soon as the current instruction is done. It saves the register state, goes to a well-known memory address, FFF8, reads the 2-byte word stored there, and jumps to it. On the CoCo, the address stored there is 010C. And when BASIC boots up, it ensures that a jump instruction is placed at 010C. That jump instruction takes the CPU to the real interrupt service routine. So there are a couple hops here. The CPU looks at FFF8, that points to 010C, and 010C jumps to the routine. The job of the interrupt routine is to do whatever it wants. Games use the IRQ to synchronize drawing into screen buffers. BASIC uses the IRQ to increment its built-in timer, handle musical note durations, or turn off the floppy drive motor after a delay. But when it's finished, the interrupt routine does an RTI. This restores all the registers and returns back to the mainline code that was interrupted. So that's the IRQ. The NMI, or non-maskable interrupt, is similar, simpler, and more complex. The NMI pin on the CPU is directly connected to pin 4 on the CoCo's cartridge slot. So raising an NMI is one of those superpowers that only cartridge software can do. Software you load from a cassette or from a floppy cannot raise an NMI. When the NMI is signaled, the CPU reads the 2-byte word stored at FFFC and jumps to it. On the CoCo, the address stored there is 0109. And when Disk BASIC boots up, it ensures that a jump instruction is placed at 0109 to jump into the Disk BASIC ROM's interrupt service routine. That sequence is similar to the IRQ, but perhaps you noticed a couple differences. For one, no PIA is involved with the NMI. Instead, whatever software or hardware sits inside the cartridge directly signals the NMI whenever it wants. Also, the condition code register has no mask bit that would allow the CPU to ignore the NMI. That last part is why it's called a non-maskable interrupt. Nothing can block the NMI. So from the hardware architecture point of view, things are simpler with the NMI versus the IRQ. But let's check out what Disk BASIC does next. The best way to understand how Disk BASIC uses the NMI is to understand this loop. This takes a sector on a floppy, and a sector is simply a subdivision and it contains 256 bytes, plus a few more we can't access for control purposes, and reads those 256 bytes one at a time. We load the B register with the next byte. We store the B register somewhere in RAM. This tells the drive to keep on going. And then we branch up to the top. Did you notice anything weird about this loop? This branch instruction is unconditional. It always goes back up to the top of the loop. This is an infinite loop. Nothing in this loop asks if there's actually another byte left to read. It just keeps on reading bytes forever. But of course, it doesn't actually go on forever. The NMI is key to stopping this loop at the right time. Before we ever get to this loop, we set things up beforehand. We store an address in the special location dnmi vc, and then we set the NMI flag. These are both special values that are stored in the Disk BASIC working area of memory in the hex 900 range. This simply indicates whether we're going to use NMI or not, and this is yet another vector. It's another hop that we're going to take in our NMI journey. So now let's finally take a look at the NMI service routine. This is it. It's really tiny. We check the NMI flag to see if we're supposed to be here, and if not, we get out. And if so, here's where we load X with the value that we stored at dNMI VC. This is the next vector. And then this crazy instruction will store that vector 10 levels deep into our stack. Finally, we clear the NMI flag and return. What? Well, the key is here. When we follow the stack pointer and then go 10 bytes after that, that is exactly where the program counter was preserved at the time that the NMI was raised. We're doing stack surgery here so that the RTI we're about to do does not return us to the code that was interrupted. Instead, we return to this other address. The code that was interrupted was this crazy infinite loop. We do not want to go back here. So you can see the purpose of the NMI was to somehow break out of this loop. And while interrupts usually return back to the code that was interrupted, this is doing the opposite. It's interrupting an infinite loop so it could return to the code it's supposed to run after the loop is complete. And that's why before we got into that infinite loop in the first place, we stored this special address at dNMI VC. That takes us here, the code that's meant to be run when we're done reading a sector. Why? Why all those weird hops and that stack surgery? The answer has something to do with that infinite loop. Typically in software, a loop is governed by some kind of variable that gets updated or at least checked each time through the loop. But in the messy world of hardware, that's not always best. Let's dig a little deeper inside that disk cartridge. We've talked about the cartridge pins, and the ribbon cable that goes out the right side, and the Disk BASIC ROM chip. But truly the heart of this is the Western Digital 1793. This is the floppy disk controller chip. It acts as the interface between the drive and the CPU. Mostly coming out the right side are all these lines that will eventually go out to the drive. And on the left side are the pins that mostly communicate with the CPU. You'll see it has 8 data lines, a couple address lines, and a few more important goodies. In fact, let's take a look at this interrupt request line. It comes out, goes through some logic gates, travels to the left, goes through another logic gate or two, and eventually ends up at the NMI pin of the cartridge port. The signal to generate the NMI is coming directly from this floppy disk controller chip. And from the 1793 datasheet, we can see that's the exact intent. The interrupt request pin is supposed to go directly to the interrupt on the CPU. And sure enough, the floppy disk controller lets us know when the operation completes, either successfully or when there's a failure, asynchronously through this interrupt request signal. We should also note that there's another way the floppy disk controller can indicate completion or failure, and that's with the busy bit that the CPU could poll. It seems like polling that busy bit would be a lot less convoluted than having an infinite loop that we need an exception to break out of. We will circle back to that busy bit, but for now, let's see exactly what actually happens. We will go step by step through the code in a debugger to see how it all fits together. I'm going to issue a dir command to Disk BASIC, and that's going to force it to read at least one sector, and so we get to see how that process works. To start with, I'm going to set a breakpoint up here. This is the code that prepares us to enter that infinite loop. It sets up our escape hatch here. This is where the NMI routine is going to return to. So let's issue the dir command. And here we are. So X currently has the value D88B, so we're going to store that into dNMI VC. So D88B is going to be the place that we end up at when we're all done. So let's go down a bit, and let's set a breakpoint here. This is that tight loop that reads the sector byte by byte infinitely, if it weren't for the NMI to help us escape. Speaking of which, let's set a breakpoint here at the NMI service routine so we can see when that gets entered. So I'm just going to let it fly, And now eventually we're here in the read byte loop. So you'll see we're reading bytes from this hardware register, which is tied to these data lines on the floppy drive controller. And that first byte is FF. And then we store it wherever X is pointing. So right now X is at hex 600. So as we go through here, we're going to be reading byte after byte and storing it further and further into that region of space. So we're going to keep on going until we get up to X at 700. So I'm going to get rid of this breakpoint, let it fly, and now we end up at the NMI service routine. So the fact that we're here implies the floppy disk controller successfully signaled the int request line, which in turn signaled the NMI on the CoCo. You'll see that X has advanced to 700, so we seem to have read everything out of that sector. We check the NMI flag to make sure that we're supposed to be here. If not, we would return immediately, but we are supposed to be here, so instead we read that value that we had stored into DNMI VC, which is D88B. And we're now going to do some stack surgery, so let's actually take a look at the stack. So the stack pointer is at 7F16, so we're going to write that at 10 after that, 10 in decimal. So that's 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So right now we have D881, and we're going to store D88B. And there it is. We clear the NMI flag since we finished it, and now if everything is done correctly, this RTI is not going to return back to that infinite loop. It's going to return here, our escape hatch. Let's see. Yay! And this process is going to continue to happen for every single sector that we need to read until our dir command is complete. So we now understand that infinite loop isn't really infinite. But there is one other huge problem with that loop I just glossed over. Let's just review. We read a byte from the floppy disk controller, write it to RAM, reprogram the floppy disk controller, and repeat. We're communicating with the floppy disk controller here and here, but this is all asynchronous. This is all happening at the speed of whatever clock is tied to the CPU. But the floppy disk controller is operating at the speed of a motor that lives in the real world. So what if the CPU is going through this too quickly? What if another byte isn't actually ready for it? How on earth could this possibly work? The solution is barbaric. The floppy disk controller has this DRQ, or data request pin, which sends a signal every time a byte read from disk is sitting in the data register ready for the CPU to consume. Similarly, if we're writing to the disk, the DRQ signals whenever the floppy controller is ready to receive another byte from the CPU to write to the disk. Check out where this DRQ signal goes. All the way to this cartridge port pin called halt. Along the way, it goes through some logic gates where it gets combined with the high bit that was written to the FF40 disk control register. We haven't talked about the FF40 disk control register, but this is yet another component inside the cartridge that allows the CPU to write values to different bits and control different behavior. The high bit of this register is the halt flag. When the CPU sets that bit, it's basically giving permission to the floppy controller to bring the CPU to a dead stop. We can see these halts happening in real time using this instrumented version of MAME. On the left, we keep a count of how many times the halt line goes active. We're going to do a dir again, and we're going to set a breakpoint here at the NMI service routine. Each time a command completes, the NMI service routine gets called, and at this point no halts have happened yet, probably because we haven't read any sectors yet. But watch what happens when I continue. 256 halts and resumes happened in just that short amount of time. My guess is that happened once for each byte that we read out of the sector. Let's continue. Another 255, maybe we were able to get a couple bytes in without a halt between them, but all the rest needed a halt. I'm going to keep on going. So we can see that these halts are happening constantly, and it's the primary way that the floppy disk controller is able to synchronize itself with the CPU. It only allows the CPU to run when there's a byte for it to read or it's ready for the CPU to write a byte. Now that we see how Disk BASIC actually works, Let's simplify things. Let's go into the ROM and hack it and simplify everything so we don't need NMI and we don't need halting. It's going to work great. We're going to conduct a series of experiments where we go increasingly different from how Disk BASIC does stuff, and we're going to do this by hacking the ROM. Since we can't actually write to the ROM, we're going to do a little trick that many CoCo programs have done. Rather than mapping the largest 32K of logical address space to the ROM, we're going to map it to RAM, and we're going to copy the contents of ROM into that RAM. In this way, the CoCo will run totally normally, but we'll have the ability to actually make writes, make changes to that ROM code since it's now sitting in RAM and we're running it from RAM. Next, we're going to prepare our floppy by just writing a single sector to it, where we write all the byte values from 0 to 255. And then we start hacking the ROM. This loop where we read all the bytes of the sector from ROM is the thing we're going to change. We're going to stamp a jump instruction right here so we jump out of the ROM, which technically is RAM, but still you know what I mean. And we're going to have a jump to here. This, by the way, is identical. There is no difference. We're just doing this to verify that everything still works, even though now we're doing our version of that read byte loop. And then the fun part. We're no longer going to allow halts to occur. This routine takes the code that would normally set that halt allowed flag and instead have it just do nothing. And now we try reading that sector without any halts at all. So let's copy the ROM to RAM. We'll write our single test sector, and you'll notice that our halt count went up. And here's the buffer of bytes that we wrote from. And you can see they go up from 0 all the way up to FF. We're going to read that back into memory to verify. And sure enough, we're still going from 0 up to FF. And next we're going to patch that read byte loop so we jump into our code. These are the familiar instructions to read a byte from disk, store it to RAM, reprogram the floppy drive controller, and branch back up. Keep your eye here, and you'll see now we're jumping to 40D4. And that, of course, is our own copy of the code, which is doing the exact same thing. So let's set a breakpoint in our copy. And let's see what happens. We're still allowing halts, so this should be working like it usually does. And if you look on the left, you'll see that the halt count continues to go up. So everything is working as expected. It's just that we're using our copy of the read byte loop rather than the one from ROM. And now we change the code in the ROM so it no longer sets that halt flag. This is the code where we're setting the high bit of the FF40 register. And one step later, and now we are no longer setting it, so this basically does nothing. So let's see what happens when we do the read without any halts. To us it looks the same so far. And as we go through, we can see that one by one, oh no! We got two 2s! So we read the 2 byte twice. Oh, we read the 4 byte twice. It's a 6 byte twice. This is not good at all. So let's skip ahead and see what happened. We have a lot of duplicate bytes. We should have been up to FF over here. We only got as far as AA. So this is telling us that the halt flag really was doing something useful. So that means that we're going to have to adjust our read loop so that it manually slows itself down. So this here is the new read loop that doesn't need to be halted. Instead, it will kind of just halt itself. To keep things efficient, we're going to put the address of the status register into the U register. This is our read a byte and then store the byte into RAM portion. What's new is we're also going to read now from the status register and ask it if it's ready for a byte. What we're doing is looking at the DRQ, or data request bit. If this is set, then that means there's a new byte ready for us to read. Otherwise, the old byte is still there, and we don't want to read that. So if it's not set, we branch back up to here and just repeatedly keep testing that bit. Are you ready? Are you ready? Are you ready? Are you ready? When it's finally ready, then we reprogram the control register, branch back up, and read that byte. So now we're ready to do this again, but this time without the halt and with our loop that knows there will be no halt and thus compensates for it. The read byte loop haltless routine. So let's continue until we get there. Okay, we read a byte. We read another byte. If you look here, we have our 0, we have our 1. Another byte, another byte. Now we're not retrying at all. Oh, we just had to retry there. To speed this up, I'm going to set a breakpoint here and just continue. And move this out of the way a bit. And each time I hit F5, we'll see if we read a byte or if we had to retry. Yep, we had to retry there. Had to retry there. So let's skip to the end and see how this does. Looks perfect. Looks like we didn't need to halt the processor at all. All we needed was just a few extra lines of assembly. So we've shown we can basically remove this connection from DRQ out through halt. Can we do the same for the connection from int request all the way out to NMI? Well, in the case of halt, we had a flag in the FF40 register that we could simply disable. There's no dedicated bit for NMI or exception or anything like that. But bit 5, which decides whether we're doing single density or double density, is related. Bit 5, the double density flag, comes out here, gets inverted, and then we see it from here go through a couple more gates out the NMI. So the cartridge appears to be tying two things together, this double density flag and whether or not to signal NMI. I believe the idea is that when the disk is double density, we're reading data off of it much quicker. And in that case, you don't want to be polling for a bit every time through the loop. You want that loop as tight as possible. So instead you want it to be infinite and just have it be interrupted. Of course, I'm not going to take that advice. I'm going to poll it to my heart's content. But I got to do something with this wiring here. So my plan is to virtually change the wiring so that this bit does not decide double density. All it decides is NMI on or off. Basically, we're always doing double density anyway. I don't want that to change. So I want this flag to continue to decide whether or not NMI is enabled. But I don't want this flag to decide whether or not double density is enabled. I just want it to always be enabled. Basically, I want to snip this line here. And since we're doing this virtually, this is simply a matter of changing a line of code in MAME. This is the line of code that writes to the 1793 the new value of the double density enabled flag. And here, as you can see, we're inverting the result of bit 5 from the FF40 flags. I'm just going to always send 0. Since double density is active low, a 0 means we're going to always enable double density regardless of the state of the flag. That way the flag is exclusively used just to decide whether or not we're going to do NMI. This is the line of code that sets the double density flag. Instead, we want to clear the double density flag, which will then prohibit the use of NMI, but because of my hack, we are always actually going to be using double density. So rather than setting bit 5, we're going to clear bit 5. The next task was to change my read byte loop, so rather than expecting to be interrupted, it would now be a conditional loop that didn't go infinitely and would simply check to see whether or not the command was completed. As the datasheet hopefully tells us, this busy bit is all we need to check. I'll be honest, getting this code right was not easy. It's very delicate to timing and everything has to be done as quickly as possible. And one of my earlier iterations would sometimes work and sometimes not. But eventually I landed on this. This is the loop that goes byte by byte, pulling it off of the disk and saving it in RAM. This is the loop that just keeps polling to see if it's ready for the next byte. This is what allowed me to eliminate the halt. Once I break out of that loop, the very next thing I do is I check the busy bit. And this is the big change. Rather than an unconditional branch that goes all the way up to the top, we now base that branch on the status of the busy bit. And we need a way to get out of here when we're done. So when the busy bit is not set, we end up here, and then we jump to the very place that the interrupt service routine was going to jump for us. Rather than using the NMI routine, which stores dNMI VC in that strange location on the stack so that we can RTI to it, we just directly jump there when we're done. So we've eliminated some wires from the diagram, and we've eliminated this entire service routine. And really only with just a couple lines of code. So the first step in our new code is to change that NMI flag. Rather than setting it, we're going to clear it. This is the line of code from the ROM that sets it, and it's now patched to clear it. Next, we're going to set a breakpoint in our new read loop right here. And this is our buffer of bytes we're going to read. And so as before, sometimes we're going to retry doing, or rather due to the fact that we're not halting, and sometimes we won't. And as we go through, you can see on the left that we're filling in the bytes one by one, sometimes with a bit of a delay, sometimes not. The key is we should never get down here until we're absolutely done. I'm going to set a breakpoint, and I'm going to hit go, and there we go. The buffer is totally filled from 0 to FF. We're down here, and if I step from here, we're where we belong. We're back in the ROM, to the place where the NMI would have returned us if there was an NMI. And if I just continue, we're all done. Wow, I sure did simplify things, and I proved it worked great. There's only one thing left to do to prove myself a hero, and that's to see how the performance compares. I'm sure this will go great. Let's compare the timing with how the ROM normally does stuff versus how I made it do stuff. We start out with the usual preparation, and then we go through a timing loop where we do 2 experiments. First is our baseline. We patch the ROM to jump to our read byte loop, but our read byte loop will be identical to the ROM. The reason we're doing the patch at all is to try to keep things similar. We need to have that jump in the next experiment, so let's keep the jump here, but we'll just jump to the loop that's identical. And then for the actual experiment, we set up our flags, and then we patch the ROM to jump to our new loop, which does all the polling, doesn't need to be halted, and doesn't need to be interrupted. And we then reset and repeat going back up to here. Both for the baseline and my experiment, we run this timing test. We simply read a single vector 50 times in a loop. And just before the loop, we signal to the Lua script that we're about to do an experiment. And when the loop is complete, we tell Lua we're done. The Lua script responds to those writes by starting and stopping the timing. It's just using wall clock time, which is in milliseconds. And each time it stops, it prints out the elapsed milliseconds. So here's a spoiler for you. This is not going to go well. See if you can actually hear the difference between the 2 experiments. So that was our first experiment, the baseline, the way the ROM normally does it. And you hopefully were able to hear a very smooth, constant spinning of the disk. Now let's do my experiment. It took a lot longer, and you probably heard a whole bunch of, I don't know what, adjustments of the head. When I debugged further, it did seem like there were several retries happening at the disk command level. There's a routine called diskcon, which I'm calling to then cause my read byte loop to be executed. And I think that it had to retry itself several times because it ran into some errors because my code just wasn't quite timed perfectly enough. And to show this isn't a fluke, let's just run a bunch more. Remember, each odd-numbered experiment is really the baseline, and each even-numbered experiment is running my code. Well, my way was simpler, but it sure functioned worse. I guess sometimes a sheer brute force approach is the best way to merge the worlds of the ideal and the real. Anyway, I had loads of fun learning about all this, and I hope you did too. Thank you for watching. Let's dig a... Because it wasn't ready for us yet? Still not ready for us? Ooh, what's going on? Not ready at all? What's going on here? Let's do this again.